Cool. All right, awesome. Welcome everyone. And in advance, thank you to our speakers, Ryan and Martin Durant. So this is going to be the first of at least two parts on sort of focused on advances in Zarr. There's a lot going on in Zarr these days, specifically focused around the Zarr V3 Spec, which is what Ryan's going to lead us off with today. So we have Ryan Abernathey. We did have Norman Zebka. I'm not sure if I'm saying his last name correctly, but Norman Zebka unfortunately had a family emergency. He was going to talk about Zarr Sharding. He will be able to, it sounds like he will be able to join the next session on April 24th. So we're going to have another great set of speakers April 24th. So please join us again then at the same time. I'm also really glad that everybody found this link. I apologize for my snafu. But yeah, basically we have a new link, so I'm glad everybody found it. Really great. And then we're going to have Martin Durant will present on variable chunking. I've also pasted a link, so I'm going to share two links before we go into other announcements in the chat. So while the speakers are giving their presentations, feel free to add questions to this Slido. Then you can also vote on other questions. So we're going to use that. So at the end, it will help us prioritize discussion topics that are the most popular. So please use that link to post any questions. Of course, if you want to post questions in the chat, that's fine as well. And then I've also posted a link to this form that I will repaste into the chat. So that form is called Defining the Future of the ESIP Cloud Computing Cluster. So I wanted to take this moment. I've been part of the cluster, one of the cluster leads for the past 2 years, and it's been amazing. It's been an amazing platform to generate ideas and community around a lot of the cloud computing things that are happening in earth sciences. And I want to continue to have that presence in community and do even more with it. So if you have ideas, requests about what types of sessions you would like to be in this community, this cloud computing community in the earth sciences, please take 5 minutes to fill out that form to help us make the most of this medium. In terms, those are sort of my announcements. I want to give a few minutes to, I think Megan Carter's joined us today for the few minutes to talk about the summer meeting.
Yes. So first of all, wow, there are 55 people here. That's awesome. Such a testament to Amy and this group and all the awesome people who convene here. So thank you. And I don't want to take too much time from your meeting, but if you're just joining us for the first time, we are a community of earth science data professionals convene around a number of different topics, including this one. And that's through monthly telecons and also through our 2 conferences that we have each year, which are in January and in July. The next one is coming up July 18th through the 21st. It will be held in Burlington, Vermont, but we will also have virtual participation, virtual presentations. We'll do as much as possible to make the remote experience as robust as we can. And in conjunction with that, our call for sessions has just opened. What's somewhat unique about the ESIP meetings are that they're largely composed of community contributed content. So breakout sessions proposed by, defined by all of you. So we really need your help to get the best session proposals in that we can. ESIP provides a lot of support to help you shape those proposals. So, it's not set in stone the minute you submit it, but we want to kind of look across what's been submitted and think about where are the overlaps, the commonalities, the people who should maybe work together a little bit more. Maybe they don't know that they've proposed something similar. So please check out our meeting website, which I'm popping in the chat right now. The call for sessions is linked there. Our meeting theme is opening doors to open science. The session proposal deadline is May 8th. And you'll see when you look at it, there are a number of opportunities to talk with ESIP staff and to kind of brainstorm and hone your ideas. So please talk with us and dream big. There's a lot of flexibility in terms of formats and ways that we can really make this as productive for you and for those who attend. So thanks, Amy, for the moment on your agenda.
Yeah, no, and I mean, it's self-serving too, because I definitely want to have an awesome cloud computing session or a couple of sessions. So if people can help me, if people have ideas that they want to propose, I'm certainly willing to take ideas and help put them into an awesome proposal in a set of sessions, especially if you're planning to be there or thinking about being there in Burlington, Vermont. Please reach out to me so that we can put together a great session. Is there any other burning announcements from the group for this community about other conferences that they want to promote or upcoming talks? Okay, well, without further ado, while the reason why we're all here is to talk more about Zarr, so I'm going to pass it off to Ryan.
Okay, great. Let's go. Thanks a lot for the invitation, and I'm excited to give an update about Zarr. I've been kind of losing my voice a little bit, so apologies if I end up clearing my throat too often. So yeah, I'm excited to present. The slides I'm going to show, a lot of them were made by Sanket Verma, who's the Zarr community manager, and I'm here representing the Zarr Steering Council, which is the governing body that sort of oversees Zarr and its specification. So, since we're sort of kicking off a session on two days of sessions on Zarr, I thought I would just start by giving some broad overview of what Zarr is. I'm not going to assume everyone here is a Zarr expert, but my focus then is really going to be to talk about the Zarr V3 specification, which is this new development that has been in the works for several years. And so the audience here, just for some context, is really people who are working on Zarr implementations, building tools that interoperate with Zarr, storage systems for Zarr, and building new specifications and standards on top of Zarr. If the specification changes should not really directly affect users very much. Like if you're just reading and writing Zarr data, many of these changes will perhaps be invisible to you. However, they should lead to improved performance and more features in Zarr in the long run. So that's sort of the audience that I'm aiming at here. And since this is the cloud computing cluster, I'm assuming we have some people here who are really interested in going into the weeds on the details of the format. Okay, so let me start by just giving a little overview of Zarr. So Zarr was created in 2015 by a guy named Alistair Miles, who is a geneticist at Oxford. And that's important for our community, just to note that Zarr is not a geospatial specific format. It's a general scientific data format that's used in many fields. It has rapidly growing user base, and it's used widely throughout industry. Right now we have 21 core developers on Zarr. These slides are maybe a year old, so that's been evolved. Zarr is fiscally sponsored by NumFocus, which is the fiscal sponsor for many of the packages in the PyData ecosystem, such as NumPy, Xarray, Pandas, etc. And Zarr has been fortunate to receive a considerable amount of funding over the past years from the Chan Zuckerberg Institute through their Essential Open Source Software program. So as I said, Zarr is a generic format for scientific array data, right? That can be data used in environmental sciences. I'm an oceanographer, so I made the figure there on the left from one of my ocean models. It's also used heavily in microscopy and genomics. So it's important to sort of establish a baseline. Well, what do we mean by arrays? What is an array format? Okay, so let's just all get clear on that. An array, multi-dimensional array, sometimes called a tensor, is a container of items. Okay. Now I'll go on record as saying, as a physicist, I'm opposed to calling these things tensors. I think the correct name here is multi-dimensional arrays. Tensors are specific mathematical geometric objects that have definitions beyond those of an array. Yet that ship has sailed. So particularly in the machine learning world, TensorFlow, tensor is the kind of accepted name for these multi-dimensional arrays there. And so we're stuck with it, and we just hold our nose and just say, yeah, okay, these are tensors. So a numerical array is a bunch of these items that have the same data type in terms of requiring the same number of bits to store, that are laid out in some kind of regular grid, right? So we can have 8-bit data types all the way up to 64 or 128-bit data types. And each little cell in here is holding one value. This can be used to store images or any number of different scientific data fields. So I think we're all sort of familiar with the idea that arrays have shapes and dimensions. So we can have a 1-dimensional array, 2D array, 3D array, up to n dimensions. And as a climate scientist, I often work with arrays that have 5 or 6 dimensions. X, Y, Z, time, ensemble member, scenario. You can really get many, many dimensions in Earth system science. And so that's why it's a useful data structure for our field. So Zarr is an open source specification format for storing chunked, compressed, n-dimensional arrays. So let me clarify what I mean there. So here's a little array, right? It's a amount of values that we can easily fit in our computer's memory. What if we have an array that's so big that we can't easily fit it into memory? We can't just hold it all in memory at once. Well, the standard way to solve this problem, used in many, many different array storage libraries, is to divide that array into chunks and compress each of those chunks and store those. And so that's how Zarr works. This is also implemented in HDF. This is implemented in cloud optimized GeoTIFF. Just about every array storage format uses this strategy for how to store really large arrays on disk. And a key part of this is that each of those chunks can be compressed, right? So you can take that piece of data, run it through a compression algorithm, and squash it down so fewer bits are being used. The catch is that using compression, generally, you have to read and write the whole chunk at a time. So this chunk becomes your sort of minimum unit of I/O operations, and that's important. So Zarr currently supports over 20 different compressors, and we're adding to this list every day as new compression methods emerge. And when you ask for some data from a Zarr array, say you want to retrieve the orange region over here on the left, the Zarr library figures out which chunks need to be retrieved from storage, decompresses those, and puts the data into memory for the user to do some computations with. Zarr allows you to organize multiple arrays into hierarchies or groups. And it also allows you to store arbitrary metadata, just JSON style key value metadata along with those arrays. And Zarr explicitly copies the array and group style hierarchical data model of HDF. So it's just sort of diving in a little deeper to what I said earlier, but the way Zarr works is each of these chunks here from my big array gets an index, which would be this number 0.0, 0.1. You can also think of that chunk as a tile if it's a 2-dimensional array data structure. When storing that chunk, the sort of raw array data get compressed into bytes, and those can be stored in any key value store. And then when retrieving the data, that same key is retrieved, decompressed, and put back into memory. This idea that you can store this data model into any key value store is a real important property of Zarr's flexibility. You can obviously put those chunk data on your hard drive, and also just keep it in memory and use this as a way to reduce the memory footprint of an application. Or you can put it into any number of databases and storage services, such as cloud object storage, Amazon S3. You can put it into your favorite key value database like Redis. The storage layer it just has to be able to set and retrieve those bytes. So here's a sort of summary of like why you would want to use Zarr. Well, because of the way the data are stored, Zarr is really optimized for highly concurrent reading and writing, right? So because each of these chunks is stored as an independent file, you can read and write them concurrently very easily. As long as you align your writes with those chunk boundaries, you can write them concurrently from hundreds or thousands of processes and read them back in the same way. And this allows Zarr to be an extremely scalable, high throughput format for big data. And that's probably where Zarr is used most heavily today. It also makes it easy to extend or append to your arrays. You just add more chunks. In contrast to some other sort of cloud native formats, such as cloud optimized GeoTIFF, Zarr is completely agnostic to how you do your chunking. It doesn't say you have to chunk in the spatial dimension or the time dimension. It's really up to the user to choose whatever chunking strategy makes sense for their application. So it's pretty flexible. The compression support is very broad in Zarr. There's almost all state-of-the-art compressors codecs are supported, and it's very easy to plug in and add your own. Zarr is very flexible about how it can store, where it can store things. You can store in local files, cloud storage systems, really any key value store. And Zarr is also just pretty simple and based on a very open, readable specification, which allows it to be hackable. What I mean by that is if you want to try out some new way of storing or manipulating or encoding data, the barrier to doing that in Zarr is pretty low. And I think this is actually the key feature of Zarr, which has led to a lot of innovation and new ideas that have been tried out in the Zarr community. So Zarr has a bunch of implementations. Zarr started in Python. It's been implemented in C++ a couple different times, a couple different ways. It's implemented within the NetCDF library in both Java and C. Julia, there's several JavaScript implementations. There's now a Rust implementation. And just about all of these are native implementations. So that goes hand in hand with the simplicity aspect that I mentioned. The Zarr specification is simple enough that most people find it easy enough to just code up a new implementation from scratch. And that may change as Zarr gets more complexity, which is going to happen. Within ESIP and Pangeo communities, Zarr is used pretty heavily as part of our sort of cloud native processing stack. So within the Pangeo ecosystem, Zarr is often our format of choice when we're doing data analytics in the cloud. Storing data in S3 or Google Cloud Storage. We might do scale-out processing using Dask. And very often the Pangeo users are using Xarrays, their high-level API. So Xarray can open Zarr data, do processing on it, and then other packages sort of build further on top of that and provide higher-level functionality. And at the base of this is often Zarr data. Some prominent examples of Zarr data in the cloud include the CMIP6 public data sets that are hosted in both Google Cloud and AWS. And there's many others, but I just picked this one, multi-scale, ultra-high resolution sea surface temperature. These are really different data sets structurally. CMIP6 has over 5,000 individual Zarr stores or groups corresponding to the original NetCDF files, whereas the MER data set is really just one giant array that occupies over 54 terabytes. So now we come to the main topic, which is the evolution in Zarr from the V2 spec to the V3 spec. So the Zarr specification is really the technical specification of the protocol used to store the data on disk. And the spec is key to allow implementations to implement Zarr and read and write that data. Over the past 6 years or so, we've gained a lot of experience with Zarr, and we've kind of realized that some things can only be fixed through a breaking change in this specification. Similarly, going from Python 2 to Python 3, Python 3 is not backwards compatible to Python 2. We've decided to make a non-backwards compatible change to the specification. And I'm going to explain why and what we hope to achieve with that. First, I want to note that doing this has required us to think really hard about the governance of the Zarr project. So this is a topic I know people here are interested in, and open source communities, we love that they're open and that they're distributed and anyone can contribute and participate. But the lack of sort of a central authority can also make it hard to take bold action in a project, right? Zarr was originally created by one person who kind of was the BDFL of the project. That person, Alistair Miles, has since sort of withdrawn from the project. The community has had to step up and come up with governance that will allow us to make these changes and manage the project in a sustainable way. A huge part of that has been the fact that we got a grant to hire a community manager who was able to just help us with so many of the logistics and process involved here. So that's Sanket, and I really want to shout out Sanket and all the great work he's done. We also created a Zarr Implementation Council, which involves all of the different libraries that actually implement Zarr. They have a seat at this council, and they're able to vote on these changes to the spec. And we think that's important because if you change a spec, but if you make a spec change, but nobody's going to implement it, I mean, there's no point, right? So we really need to have those implementers at the table. And finally, we created a process called the Zarr Enhancement Proposal that, similar to Python enhancement proposals, PEPs, or NumPy enhancement proposals, this is a process by which we can evolve the spec and make changes and ratify those changes. And this is really hard work to do this stuff. It's a lot harder than just writing software. And I would say we've learned a lot in the process. It's been pretty slow. So some of you may have been waiting for Zarr V3 for 2 or 3 years or something like that. And this is why it took so long. It's a lot more than just writing the code. I really want to shout out the 2 authors of the V3 specification, Jonathan Strebel and Jeremy Mateen Shepard. These folks are the ones who really actually pulled it all together and sorted through all of the hard questions and pushed the V3 spec forward through a lot of really diligent work over the past 6 months or so, and Sanket as well has been a big part of this. Okay, so let me explain the motivations, why we had to make breaking changes to Zarr V2. Well, a big part of that was, did I miss a slide here? Okay, now, these are in a reverse order. Okay, so I'll start on this slide. A big part of this is interoperability. So I mentioned that Zarr originally started as just a Python library, and then it slowly became implemented in other languages. It sort of merged with something called N5, which is originally, I believe, a Java library that did a very similar thing. And what we realized along the way is the V2 spec really contained too many Python-specific things. Like it referred specifically to how you would store Python object D types, right? And that just really didn't make sense for a multi-language, language agnostic specification. So V3 is sort of scaling back its support for that type of thing, so that all of the data types that are part of the core spec are things that any programming language could reasonably be expected to understand and implement. And as a result, the new spec will be truly language agnostic and more narrowly scoped. And the goal is that we can achieve full interoperability and feature parity across all languages that implement Zarr on the core specification. Another key reason for the spec evolution is extensibility. Now, I mentioned that Zarr is highly hackable. And what I really mean by that is you can develop a fancy codec or a store implementation that will do just about anything you can imagine. A great example of this is the Kerchunk approach to creating indexes, Zarr indexes of data that live in netcdf or HDF files. it's possible to do all kinds of things by sort of hacking Zarr. However, ironically, there's no way to formalize any of those things into actual specifications within the Zarr V2 framework. It just doesn't have any extension points. That's a big problem. So what we are doing with V3 is explicitly defining extension mechanisms that will allow some of these sort of hacks, these sort of really innovative and novel uses of Zarr to mature into a formal extension that's written down and that can be implemented by other languages rather than something that's just sort of only exists in code. So extensibility is huge. Another motivation is the emergence of high latency storage, by which I really mean cloud object storage, right? So we think of Zarr as a cloud native format, and it works very well in the cloud today. But the specification and the way things were organized within Zarr was developed originally with local file storage in mind. The big difference between cloud storage and local file storage, the cloud storage has much higher latency than local file storage. It can be 100 milliseconds before you even can get a single byte back from object storage, right? So V3 contains some subtle changes that should allow us to achieve much better performance with cloud object storage by removing certain assumptions that had been baked into V2. And finally, we are explicitly creating the possibility of more flexible storage layouts. And an example of this is this so-called sharding feature, which allows us to pack multiple chunks into one object or file. And I'll mention more about that later in my talk. Norman was going to give a whole talk on this, but he had to cancel. And we'll hear from him at the next session. So these are the motivations. Now, I'm just going to start sharing some details of the spec with you. Mostly this slide is just to explain where can I go to actually see the spec, right? Well, so there's two main parts to Zarr V3. There's the ZEP, the Zarr Enhancement Proposal, which is a document that sort of describes the motivations and the scope and the high-level impacts of this new spec, sort of like why are we doing this? And then there's the core spec itself, the V3 core spec, which you can find at the links above. And then there are additional sort of supporting documents there about the codecs and the stores. We're just trying to write more stuff down about how Zarr is actually implemented as part of this process. Okay, so for those who really want to be in the weeds about how Zarr actually works and stores data, here's kind of my most technical slide that explains how Zarr V3 will store data. So the names of metadata documents have changed from .zarray and .zgroup. Now we just have a single Zarr.json where metadata are stored. We are now, by default, storing chunks in a subdirectory with the prefix C. And those may seem like small things, but then we also have the ability to configure many of these parameters, such as these prefixes and separators, as part of the configuration. And that should allow tuning the storage, keys to meet different requirements of different storage devices. Let me say a little bit about extensions, right? So extensions are a very exciting part of this. So extensions add new features to Zarr itself, which may involve changes of how the data are stored, encoded, or processed, right? And so we can have different there's basically, currently 5 clear different extension points where you could add an extension to Zarr. You could create a customized data type. So for example, to get back those Python object data types, we could create an extension for storing Python objects in Zarr, but that's not going to be part of the core specification. That's going to be an optional extension. And if people don't want to implement that in C++, that's fine. Chunk grid extensions. Martin's going to talk about one of those. These are going to give us more flexibility in how we organize these chunks. Chunk key encoding, codecs, and storage transformers. I'll give you a detailed example of the last one on the next slide here. So this is an example extension that's currently in the works. It's ZEP2 and it's called Sharding. And I think some of you have probably heard about this. So Sharding is an example of an array storage transformer. So an array storage transformer is something that basically looks like a store. It takes a key and it returns back data for that key, but it then passes its request on to the next layer of this chain of storage transformers, ultimately reaching the underlying storage device. And so what this extension does is it allows many chunks to be stored in one single file or object, which we call a shard. And this resolves one of those core problems that I mentioned earlier, where if we have, potentially, if we have a really large array, it can have millions of chunks associated with it. Or if we want to use really small chunk sizes, we can get millions or billions of chunks. And as long as we have to store those one-to-one in files or objects, our storage device is not going to be very happy with us, whether it's a file system or object storage. So this allows us to break that one-to-one correspondence between chunks and files and pack many, many chunks into one file. This allows reads to be performed concurrently against the individual chunks. However, writes still have to be performed concurrently against the shard. Otherwise, you need some sort of locking mechanism here. So there's a whole talk on this, how this is going to work by Norman, and we'll hear that next time. But we're really excited about some major performance enhancements this is going to deliver, particularly on reading scenarios where you have to either subset large arrays, extract points, or do interactive visualization on large arrays. So the status of V3 is that it is the draft is now complete as of, I think, today. All of the comments that have been collected and everyone who's, dozens of people have weighed in on this and commented and made suggestions, and we've iterated for months and months. And the next step is that the ZEP has to be implemented, or rather approved by the Zarr Implementation Council. So we're really finally getting there on Zarr V3, and it's pretty exciting. And of course, what comes next is the community gets to work on all of these extensions, which is, I think, what a lot of us are excited about, the potential that those extensions offer. And that's what I think many of the other talks as a part of the session are about. I'll wrap up there. I just want to just mention for everyone here, Zarr is a completely open community. There's a lot of work to be done. If you want to get involved in an open source project, we could use your help. And we have bi-weekly community meetings where we just talk about the project status, and anyone can come and raise questions. And of course, we're on all the socials and the GitHubs and all of that stuff. And so we just really welcome involvement, questions, and we're actively looking for new community members to join Zarr. Okay, so that was a bit dry and technical, but it hopefully gave you some idea of what Zarr V3 is and why it was created. And I guess we'll stop there and we'll move to the next speaker.
Nice. Martin, do you want to go ahead?
Yeah, okay, I can go straight in. My thing's going to be much shorter and simpler, though, so I hope that's all right. Let me just rearrange my windows. One moment. Okay, so I should introduce myself. I am Martin. I work for Anaconda Open Source, and I've been in the Zarr community for quite a long time. I'm not as deeply involved in the planning and steering as Ryan and other people, but I've been around. My areas of interest around storage, which means keeping bytes in a particular place and how those bytes are organized, and parallel access to them, and parallel processing with Dask. So those are the things I've been involved with. ZEP 3 is a pretty simple proposal, and it's about the chunking, as Ryan already mentioned. So this is how things are stored at the moment. This is, I guess this diagram was built for V2, but it's not conceptually different for V3, in that you have groups. In those groups, you can have arrays, one or more arrays, you can have more groups. But in each array, you have these chunks. And the chunks have simple indexing pattern, 0, 0, 0, 1, etc. And critically, each of these chunks has the same size. So in this case, if each of these chunks is 20 by 50, then the shape of the whole thing is 60 by 100. And you can figure out for any particular XY index which pixel of which chunk you need to get, very simply. This is the two-dimensional case. It's the same for however many dimensions you happen to have. Now, by contrast, this is a Dask array, and Dask is commonly used for processing Zarr, but not necessarily. But Dask arrays are quite similar in that you have a logical global array, and then you have many small pieces that make it up. But the critical difference for this presentation is that the shapes of these things inside are not all the same. They're all rectangular, and you can see that they all align along these horizontal and vertical lines. Again, this is the two-dimensional case, which is easier to represent. But actually, the chunk sizes along each of the dimensions varies from one chunk to the next. In this case, the chunk prescription would look something like this. Instead of just having a single number for X and a single number for Y, you have a list for each, but you do still have a defined shape, and you still have a uniform D-type over the whole thing, as you would expect. In this case, if you wanted to know the value of a particular pixel, you need a little more logic to figure out which chunk it lives in and which index within that chunk it is, but it's not that complicated. And the code for doing that already exists in Zarr. So the proposal will be to apply this to Zarr. But I do want to mention Kachunk. That also came up briefly. I guess people here might have heard about Kachunk. So Kachunk is a project that I've been leading for a little while now. It's about making non-Zarr, potentially Zarr, but also non-Zarr archival file formats appear as if they are Zarr, and it does this by scanning those files and figuring out where their individual internal C-like compressed chunks are, and then writing a mapping basically from where you would expect a particular chunk to appear in a directory structure for Zarr to where this byte range actually is in one of the source files. So this is the sort of diagram that shows this. Each one of these bigger rectangles might be an HDF5 file, for example. It has some metadata in, and it has these blocks of binary data, this gray thing. And in order to make this into a Zarr-like dataset, you need to know what is the structure of this whole thing. So you need to know what is the combined shape of a particular variable, and for each of its internal chunks, which file and where in each file it is located. So that's what Kachunk does, and it allows you to have cloud native like access patterns to formats that are not really themselves cloud native, such as HDF5 that you will know about, but also several others like TIFF, GeoTIFF, NetCDF3, and FITS, and others that are still being worked on. So that's the background, and the reason that it's important here is because if we have chunks in here, these individual binary buffers that don't happen to meet the restriction in Zarr that they have to all be exactly the same shape, then Kachunk just cannot represent them in Zarr. So the proposal is to make the Zarr chunk layout be variable in the way that it is for Dask arrays. So each chunk is still a rectangle. You have for any particular X, you have a well-defined shape of each of the chunks along there. And you need, the only thing that you need to describe the whole chunking scheme for the whole of an array is up to a list of chunk sizes in each of your dimensions. So that's a list of one-dimensional lists. Which was what was this thing here. This is in 2 dimensions. That's what I mean. Okay, so why would you want to do this? It's obviously extra complexity. I came at it from Kachunk. There are simply data sets that without this we cannot view. And that's because for Kachunk, you cannot change the original chunking. You're stuck with it. So if that chunking does not meet Zarr's restriction, it's just out. But this small change will allow you to see, for example, things that like you might have a chunk that is 1 chunk per month, but the data values are per day. So obviously those chunks are going to have a different size, but it's only along the 1 dimension. So it's actually a really simple data set to understand, but currently Kachunk can't handle that. And you will also tend to get this if you have your sub files that you're scanning over to make a single logical data set. If they have the final chunk is not a complete chunk, which is pretty common, then you just won't be able to represent this using Kachunk. It turns out there are other use cases, and that this idea had been discussed before I started talking about it. So you would need this, for example, if you have ragged arrays, such as awkward arrays or sparse storage might need, where you have a number of related arrays, maybe offsets and data, and you, in order to be able to sensibly load a single set of arrays together, you need them to have the chunk break in the same logical place. But because these are ragged arrays, the actual number of elements in each of the chunks won't be the same each time. We can talk about that separate. That's a topic unto itself. But there are some more simple cases where you might also want this. That is, if you know you're writing a big, long, one-dimensional array, but you don't actually know what size your chunks are going to be, you'd still like to write them in parallel. So you can write all of those chunks. They all end up different sizes. And at the end of it, you write your metadata saying what sizes did you actually get. Then you don't need to have locks. You don't need to do rechunking. You can just go in one go. The third one here is an interesting one. Your data set is not necessarily just a uniform grid where the data is existent everywhere and has similar characteristics. You might have areas that are sparse, you might have areas that are missing, you might have areas that you want to do special things for. So it can be quite convenient in such a case to be able to specify chunk sizes that are different in different areas of your data set. And finally, this is kind of the same as the irregular chunks for sparse storage. If you have data, table-like data, and you're going to filter it, then you're going to lose some of your rows, which means that you're going to end up with a different number of rows per original chunk. And again, if you want to do this in parallel, that means you're going to need variable chunking. A possible implementation, there are lots of ways you could do this, but in the ZEP, this is how I describe it. We already have the shape and chunk shape defined in the metadata. I'm calling this .z array. This is kind of V2 naming conventions around here, but it's going to transform just very simply to V3. It could also be implemented, backported to V2. That's a separate conversation again. So instead of having each of your chunk elements be a single integer, now we're going to have it be allowed to be a list. And that is the chunk sizes along that particular direction. This is the simplest way that I can think of to describe it, and it more or less mirrors what Dask does internally, how it describes its arrays. And the major pro is that it's pretty simple to understand and implement. Obviously, the indexing part, the actual what do you do with this would be a coding challenge, but not a very complicated one. There are some possible downsides to using the simplistic way to store the chunk sizes. The metadata file itself might grow big in some cases. I don't really see that happening because obviously you have much fewer chunks than you do, much fewer values of these chunks than you have actual values of your array. That's the whole point of using Zarr in the first place. But also you're only chunking along each of the one-dimensional axes. You don't have completely arbitrary chunk sizes. That means that you're going to have a set of one-dimensional numbers to store, and the total number of chunks that you might have along a dimension could be, you might have 1,000 chunks or something, but you're not going to have much more than that, which means that your metadata file size, well, it wouldn't fit very nicely in a text editor, but it would still be fine for loading. But I think the more serious one is if you're writing and updating an array and it has variable chunks allowed, then you're not going to be able to update your metadata at the time that you write your chunks. You're going to need some kind of consolidation or locking mechanism to be able to do that sensibly. So that's it. That's ZEP 3, and we can talk about this, but I suspect there's a lot more to talk about from Ryan's presentation.
Awesome. Thank you so much, Martin. So I think with that, I'm going to jump right into questions since we only have 10 minutes. So the first question, I might make it a little bit easier if I share my screen so we're all looking at the same thing. So the first question that I have here is, how well does Zarr accommodate non-array metadata that supports and describes the data, object, or collection?
Yeah, that's a great question. It's a very important part of Zarr. Zarr supports attaching arbitrary key value metadata to any array or group. It does not have any opinions about what should be in that metadata. That is up to a community of practice to define. And that's actually one thing I left out of my presentation that I wish I included, is this concept that we're working on in parallel to the extensions called a convention, which is simply to document a sort of domain community of practice standard around what metadata to store in those fields. So there are a lot of such conventions in use today, kind of in an ad hoc way. For example, we store CF conventions, netcdf CF conventions in Zarr all the time. We just map the attributes, one-to-one from what they would be in netcdf to what they are in Zarr. And that works great. So it's very general. Anything that can be encoded in JSON can be stored in that metadata, and it's completely unspecific about what you should put in there. And so I think it's an interesting place where we can have multiple different file containers, say HDF or netcdf or Zarr or even maybe GeoTIFF, that could hold the same data and the same metadata, right? And so I think the challenge of how do we actually specify that metadata is the really hard problem, not can the format store it, because all of these formats can store metadata.
Nice, thanks. If anybody has any questions that pop up as a result of these answers, also feel free to raise your hand. What is the best place to ask about possible new Zarr extension prior to submitting a draft?
It's a great question as well. So for really informal stuff, we have the Zarr Gitter channel. It's like a chat room. You can find a link to it in my slides or on the Zarr website. If you are considering an extension, the ZEPs repo would probably be a good place to start a discussion. I'll drop that in the chat here. We haven't had that many extension proposals yet, but that's probably a good place to start. There's also the Specs repo, and I'm now, as I'm saying this, I'm feeling like we have maybe too many repos, but you can also put your question in Zarr specs.
There is also a regular community meeting. So if you want to come and just ask and get opinions from a number of people, that might be the fastest. And I don't have the link immediately, but on the Zarr documentation, the Zarr community documentation, there are links there. So there's a standing invite available.
Okay, cool. Next question is, combining Zarr chunks together into shards sounds like reverse engineering netcdf from Zarr. What are the advantages of a sharded Zarr over chunked netcdf?
It's a great question. I think what we've realized over the past years is that fundamentally all of these formats are very similar, right? There are chunked compressed data somewhere in a file, and there's metadata, right? And so the advantages that the sharding format offers over netcdf, ultimately, there are. I want to think about how to say this. If you have a properly sharded netcdf, so it's important to specify here that the idea is not just that you have the whole Zarr in one single shard, right? So whereas netcdf is a single file, Zarr, you can have many shards within which are many chunks. So you can achieve the same functionality using netcdf together with another standard like NCML or some way to state that these netcdf files are all actually part of one larger data set. In Zarr, that's achieved by having many shards that are all part of the same array. So there are two different ways to get at the same thing. I don't think on a technical level for reading like read-only use cases, I don't think that reading the shards, the sharded format will be faster or slower than reading chunk netcdf using kerchunk. I think ultimately they're doing the same thing at a basic level. So it's really more about what those implementations can do and which software libraries you prefer to work with. And by the way, I'm not saying everyone should stop using netcdf either. netcdf is a really great format that is very useful in many, many different use cases. So I hope that wasn't implied.
Cool. With sharding, does it make sense then to always have small chunks? Is there a use case still for larger chunks?
That's a great question, and it's going to require some experimentation. In general, what we observe with Zarr today is we achieve the best throughput for large data processing tasks when we have large chunks. They order 100 megabytes. That's a good, piece of data to throw at your computer to have it chew on. And if you're trying to, process many terabytes of data, you want it to be chewing on a lot of big bytes of your array rather than a bunch of tiny ones. Now, it should be possible for us to build efficient pipelines to retrieve a bunch of tiny chunks, decompress them in parallel, and give them, to the CPU to process. And it may be possible to make that difference kind of just go away through some good software engineering. But that's really an implementation question, whether we can make the software not care. But the downside for having many small chunks is just the overhead of processing all those little chunks when you have to process a really large volume of data. So that's the trade-off.
Cool. All right. I think we probably have time for one more question. So let's go to the one that we haven't gotten to, which is, with the concept of sharding taking shape, is there an opportunity for versioning of data adds/changes to be attached to shards, creating a version stack?
Maybe I'll let Martin take that one.
I think you might have opinions on it yourself. It's not actually connected with shards so much. You already have chunks. So you can have versions of the individual chunks of a data set, conceptually speaking. How you go and organize that is not currently within the Zarr specification. So Zarr itself doesn't have a view on that. But there's lots of ways that it can be arranged. There's a proof of concept showing that you can do this simply with a Ka-chunk manifest if you want to, with a very ad hoc workflow that just shows you that such a thing is possible. It's not nowhere near production ready kind of thing. But you can definitely sort out a more thorough versioning strategy if you have the means to do it. So I don't know if you what you want to say about it, Ryan, but
I would say, I would add that there's an ambiguity over whether the versioning should happen at the Zarr level or at the key value store level, right? Like if you're storing Zarr into a key value store, you could put your versioning there, and you can just say, okay, I'm getting this version of the key value store, and so it's not obvious to me where in the stack that needs to be implemented. And I think there's a lot of people experimenting with different approaches right now, including us. But I mean, this is one of the things about opening up to extensions. Like we want people to be able to experiment and try things out and discuss them openly. And now we have a mechanism to do that. So if you have ideas about versioning and how it should look, let us know.
Awesome. Well, thank you guys so much. This is a really great session. I think I'm going to have to go back and listen to all your answers so that I can actually capture the information that you just viewed. But yeah, thanks so much for everyone for joining. Again, we have another session April 27th. I'm sorry, April 24th on this topic. So we're going to have Norman, hopefully for that one, of Scalable Minds to talk more about sharding, which is obviously of interest. We're also going to have Hailing Zhang, and I hope Brianna Pagan can also make it on to talk about the GeoZarr spec. So if this topic is of interest to you, which obviously it is because you're all here, you should join us on April 24th. And yeah, I think that's it. If you again have any ideas for the ESIP summer session, please reach out to me. I'd love to hear your ideas, and we can put together an awesome session, especially for those of you who are going to be in Burlington. So thank you so much, everyone. Yeah, thanks for joining. Bye.
Thanks, everyone. I'm going to end the meeting now. That was great, Amy.
Yeah. And right on time too.
I know. All right. See ya.